So hello everybody, today we are going to discuss about a new topic where we are actually going to address the issue of supramolecular chirality in nature. Now chirality is a very interesting phenomena, as we know, starting from an atom which can rotate into different directions and therefore have got two possible spin orientations, clockwise or anti-clockwise. The left-handedness or the right-handedness, it starts from the atomic level to fairly large galaxies which also have got these spiral arrangements. Chirality seems to be very much intrinsic in the universe. So whether it is the atomic motion or whether it is the motion of the spiral motion of the galaxies, the handedness of the rotation, whether it is the left-handed or the right-handed, sense of rotation decides the sense of chirality. So chirality is kind of embedded into the very fabric of the universe, and it has been observed that starting from a simple aggregation of molecules which can form chiral arrangements to form larger molecules, and we can have covalent bond formation where you have got stereogenic centers, where within the molecule in the covalent framework you have got different chiral centers, or you can also have a chirality which is created by the different chiral arrangement of molecules, that which gives an arrangement of molecules where a set of arrangement does not have the mirror image symmetry of that particular arrangement. So once you have a particular, say, helical arrangement of molecules, say this is one particular helical arrangement. Now I put a mirror symmetry. This is the opposite helicity. So say one is, for example, if I were to say this is left, this is right helicity. So this is a chiral arrangement. This is one chiral helix, this is another chiral helix, and on this particular backbone we can either have the covalent connectivity, or you can also have the molecules which are connected via non-covalent interactions. This will give rise to a chiral solid, a chiral compound, a molecule, whereas this will give rise to a chiral supramolecular chiral unit. So we can have these helices which signify chirality, which is associated with covalent bond formation, or where the molecules are connected in a non-covalent sense to give the supramolecular chiral building blocks. It is also to be kept in mind that in the case of the covalent association, you need to introduce the chiral information at some part of the molecule, whereas in the case of the supramolecular chirality, the molecule per se need not have any chirality associated with it. It can be an achiral molecule. M can be an achiral molecule, which I am using here, but the arrangement of this M via the non-covalent interactions creates a helical structure, which is a helical supramolecular association, and hence the resulting arrangement of molecules is chiral in nature. And it is important to look at supramolecular chirality, because supramolecular chirality is very much present in all crystals, all the molecules which associate in the solid state. And when you have chirality, it is basically characterized by the absence of a center of inversion or the absence of a mirror symmetry. So the mirror symmetry is absent, otherwise it will generate the enantiomer of the opposite handedness, and both the enantiomers will exist simultaneously in the solid state, and then the resulting solid which will be obtained is not a chiral solid. So it is important to keep in mind that chirality in a molecule can lead to chirality in solid, and it can also lead to non-chirality in solid. So just when you have a chiral molecule, there are possibility of both chirality in the solid, because now you have only one particular enantiomer which is forming a chiral arrangement by non-covalent interactions, and the arrangements can be such that you will actually have the mirror symmetry present. In that case, it will generate the opposite handedness, and therefore it will lead to a non-chiral solid. And if you have an achiral molecule, definitely you can have again a chiral arrangement. That is just like as I mentioned here, you can have a achiral molecule, but you can have a chiral arrangement. You can have a achiral molecule and you can have a non-chiral arrangement. And by and large in solids, they are also characterized by the presence of a center of inversion, which we call as centrosymmetric, or absence of center of inversion, which we call non-centrosymmetric. But overall, the mirror symmetry must be absent in the crystal packing, and these kind of helical arrangements are characterized using the screw axis in crystals, which consist of n-fold rotation plus 1 by n translation. So, you have in these helical arrangements, essentially you have, for example, if you have a 2-fold axis plus a half translation of the unit cell. So, you have, say for example, this particular object A, and you can rotate it by 180 degree, okay, and then you can actually translate it by half. So, say it comes here, then it comes here, then it comes here. So, this is related by we call this a 2-1 screw axis, where 2 indicates the n-fold, that is 180 degree rotation followed by half translation. So, that means this connectivity now creates the chiral arrangement. You can also have a 3-fold axis plus T by 3 translation. You can have a 6-fold axis plus T by 6 translation. You can have a 4-fold axis plus T by 4 translation. So, that tells you that starting with a particular molecule M, you are going to first rotate by a certain angle, say 90 degree, then you are going to translate by T by 4, then from there you again rotate by 90 degree and then translate T 4th. So, you have come to T by 2. Okay. So, in this way you will be able to have arrangement of molecules at all these points, and that connectivity will now create the chiral helices. So, these chiral helices which we have drawn here can actually be present in the sense that they are connecting the molecules using either, we can say, any of these 4 given combinations, and therefore the resulting arrangement of molecules is called a chiral arrangement, and that is the origin of supramolecular chirality in solids. So, let us compare molecular and supramolecular chirality. For example, in the case of a molecule, the actual composition is based on the atom, but here it is the molecule or the building block which are connected by non-covalent bonds. Here the bonding is covalent. Then the chiral geometry, here is a tetrahedron, an axis or a plane, where in this case this is helical, spiral, a chiral sheet or different chiral domains. So, 1, 2, 3. Manifestation of chirality is with respect to a point, axis or a plane. Here it is with respect to the conformation, the secondary and tertiary structure and helicity as we observed. And then we have got different kinds of chirality. For example, we have got induced chirality. For chirality to get induced, you have to have a chiral molecule. So, necessary for an achiral molecule to have a strong association or interaction with a chiral host through non-covalent bonds, and that will actually create the necessary chirality in the resulting structure. Then we can also look at helical chirality, which we have discussed. That is, you have an axis about which the substituents are spatially arranged so that these are non-superimposable on the mirror image. And how do we actually study these chiral domains? How do we actually look at chiral domains? There are different techniques by which we can actually understand association of molecules to form a chiral arrangements, not only in the solid, but it can also manifest in terms of the external appearance of molecules which have crystallized out. So, the process of crystallization itself can result in the formation of helical kind of fibric aggregates, helical kind of morphologies, fibrous networks, fibrillar networks, helical arrangements, helical networks, and also you can have sometimes gel like structures which are found, which has got the helical fabric arrangements internally present. So, this you can have internal arrangement and you can have the external morphology, which is the physical appearance which you see when a compound of interest has been crystallized from saturated solution, and these can actually be now imaged or viewed using different microscopic techniques. For example, we can use AFM, we can use STM, we can use SEM, and we can use TM. So, we different imaging techniques. This is the AFM technique, which is the atomic force microscopy. This is the scanning tunnel microscopy, and this is then the SEM, and then we have got the TEM techniques also. These are the other different microscopic techniques, and the measurement here involves the force between a cantilever and the sample of interest, and what you are imaging is a 3D surface, and the coating is done on mica silicon flat surface. In the case of STM, we are using electron tunneling, of the tip, electron tunneling of the tip and the surface. It is again a 3D surface imaging, and the surface is called HOPG, which is highly oriented pyrolytic graphite. HOPG is called highly oriented pyrolytic graphite. Then in case of SEM, we have got the scattered electrons. This is the basis of the measurement. We get a 2D photo, and it is a grid which is coated with gold or carbon. TEM involves absorption and diffraction of electrons. Again, it is a 2D photo, and it is put on a copper grid or a grid which is made of carbon. In addition to this, if you would like to understand the bulk arrangement in crystals, then X-ray diffraction, single crystal is the technique of choice, which will very clearly give you the arrangement of the molecules in a chiral manner, so that the resulting solid is a supramolecular chiral solid. And you can also look at the conformation and the network of interactions which create these helical arrangements inside the crystal, and that is the internal supramolecular chirality using XRD. And then there are other techniques, for example, circular diachroism, and then we have got VCD, vibrational circular diachroism, and we also have Raman spectroscopy to analyze. So there are different techniques, and in this regard circular diachroism is a very useful technique which is used to understand the presence of chiral structures of a particular handedness, and it has been observed that depending on the chirality, the magnitude of the Cotton effect is going to be same, but the sign is going to be reversed depending upon the chirality or the handedness of the chiral solid which has been formed, or the chiral association which has happened. So with this background in mind, we would like to take up some important examples of helical aggregates which has been probed using different imaging techniques. So first of all, let us consider this particular molecule here, which is a fairly large molecule, and you can see that with respect to the benzene ring, it has got this tetra, so it has got these tetra-thiofulvalene units. It has got this tetra-thiofulvalene units, and it has got the C3 symmetry. These are the C3 symmetrical molecules, but then at this position you can see that you have got the chirality which is present because of the R prime groups. And so what has been observed from this is the SEM image which has been recorded, and in this SEM image you can very clearly see the formation of the helical aggregates. So when this particular compound is crystallizing, it forms this kind of helical aggregates, and it has been ascribed to the formation of these kind of intertwined helices which form this kind of helical arrangements. Then we can take another interesting example here, in which we have considered this particular compound. As you can see, it has got chirality here, and this is a achiral molecule. This is a achiral molecule, this is a chiral molecule. So normally if you were to crystallize the achiral molecule, it will form these kind of sheets. It will form these kind of planar sheets. But now when you are actually doing the crystallization of 5 mole % of 99, these are the bis amides with 95% mole percent of 98. So, we have this compound 5 mole percent of this with 95 mole percent of this, and we have this achiral, we have this this is the achiral unit and this is the chiral unit. And when these two have been mixed in this particular composition ratio, then what has been observed by looking at the SEM images, that you have now got twisted ribbons of very high aspect ratio. That means one of the dimensions, say the length, is very long compared to the thickness of these fibers or these ribbons. And what actually prompted this chiral association, in order to understand the chiral association of this particular composition, which actually has almost 95% of the achiral component, but just 5% of the chiral component, and to understand the origin of chirality, as to how this mixing actually promoted now the chiral association to develop. And you can see this is how the resulting chiral association is now being formed, because you have now the achiral solid, but you also have the achiral solid present. We have the achiral solid as well as the chiral solid. So, the presence of the chiral centers actually now template the formation of these helical arrangements when this mixture is being crystallized together. So, what was proposed is that the presence of stereogenic centers in the co-assembly provoked the chiral propagation of the hydrogen bonding of the amide functionality thereby reinforcing the formation of twisted ribbons. And this approach is referred to as the sergeant and soldier approach. So, the sergeant here, which is the chiral solid, the minor component, extremely less concentration, directs the large army of soldiers and gives them the necessary instructions, or provides the necessary information by which they can actually now self aggregate or self assemble to form this kind of helical structures and this kind of twisted ribbons. And this is a very popular approach to understand the origin of supramolecular chirality in crystallization of compounds, where we add another component which actually is chiral, present in a minor concentration, but which can favorably now trigger the formation of bulk structures of bulk units which resemble the twisted ribbons. And if you look at the figure A, it has been obtained in this ratio 95 to 5% mole ratio in case of A, and B the images have been taken. In case of C it is 90:10, and in case of D it is 85:15. So, as you increase the concentration of the chiral component, it leads to increase concentration of these chiral units or these twisted ribbons which will be further crystallizing out in larger quantities. So, there is an increase in the population of these chiral aggregates as you increase the concentration of the chiral component, the chiral bisamide in the crystallizing chamber. So, with this way you can induce or bring about supramolecular chirality. We can take another example of this particular molecule here, and this is actually a dish shaped molecule. This is a disc shaped molecule. It has got these long alkyl chains OC10H21, and it has got an imidazole unit. And this imidazole unit gives some kind of asymmetry to the molecule. It creates a certain kind of an asymmetric environment in this particular molecule, and when we actually try to crystallize this compound in 2-methoxy ethanol, it leads to the formation of gel like fibers. So, you see these are the fibers which are obtained, and in this you can also see the helical structures which are formed, and this crystallization was done at 20 degree centigrade. And so this is the TEM image of this, and this is the corresponding AFM image of these twisted nanofibers. You can see both the left handed as well as the right handed fiber which has been crystallized during the process of gel formation. So, and then the fact that you have got both the left handed and the right handed fibers was characterized using circular diachroism spectroscopy, where you can see clearly that you have got both the positive Cotton effect and the negative Cotton effect corresponding to the different chirality, the left handed and the right handed fibers which is present, as you can see here from the CD studies. So, what does the imidazole group do? It basically increases the imidazole group, it increases the asymmetrical characteristics of the building block and promotes hydrogen bonding as well, and hence you are able to achieve, and hence we can achieve chiral symmetry breaking via the steric effect of this unit on gelation. So, the process of gelation favors the formation of these chiral twisted nanoribbons of both handedness, and therefore, we are able to achieve chiral symmetry breaking via the steric effect of this imidazole group. So, these are some of the interesting examples we have, and I hope this impresses upon you that supramolecular chirality is very much intrinsic, and in the literature there are a large number of examples which actually demonstrate supramolecular chirality in different kind of chemical as well as biological systems. So, with this we come to the end of this lecture on supramolecular chirality. Thank you.